means is that, in this case, the vector has to rotate 360 degrees to get back to itself. And in a pneumatic, the line only has to rotate 180 degrees to make a continuous field. And then the one that is familiar for superfluids is a vortex, which is a defect in the phase of the condensate wave function. If the phase changes by 2 pi, then that corresponds to a flow of fluid around it. And then the last example I'll talk about is a defect in a field of tetrahedra, which looks kind of neat because the tetrahedron has a lot more symmetries. So all these defects are configurations of a field that breaks some kind of a symmetry. So you can imagine that you have a Hamiltonian describing that field. Yeah, let me add a little color. Let's see, the green. Yeah. So if you have an order parameter, it usually wants to be uniform. And if it's not uniform, there's a cost from a variation, which you can call the elastic energy, or in the context of condensates, it's the kinetic energy. Then you have some kind of a function that prefers certain forms of the order parameter. So the order parameter can have more than one component. In a superfluid, it's just one complex number. And in this vector case, it's 2 real numbers, or so on, different number of parameters. And the minimum, if the minimum of V is some kind of a manifold, then you can have defects which correspond to closed loops going around that manifold. So I wanted to think about I'll just start by saying, let's imagine a field of tetrahedra. What kind of defects would you have? That's a neat question because tetrahedra have a lot more symmetry than like a vector field. You can draw a tetrahedron in 2 different ways. You can either draw it pointing up, when you see that it has the symmetry of a triangle, or you can draw it with an edge pointing up. And if you draw it that way, it has a 180-degree symmetry about this axis. So altogether, the tetrahedron has a non-commutative group of symmetries, and each of those symmetries corresponds to a possible vortex you could have. So that could be an interesting problem to study, and then I'll show how it actually comes out in superfluids. But in real life, any symmetry is probably broken. Maybe there's a stray magnetic field that wants these tetrahedra to be pointing in a particular orientation. Does that mean that one of these 2 types of defects is just going to suddenly completely disappear? Even if that magnetic field is really small, you suddenly can't have, it seems like you suddenly can't have that defect. So how is it possible for things to vary continuously as a function of the magnetic field? Just the blue guy. So just imagine adding an asymmetric term, which represents the magnetic field, that prefers a particular orientation. Maybe it prefers the tetrahedron to be in this orientation, so that you can only rotate it 120 degrees. You can't rotate 180 anymore. What happens in that case, it will turn out, will be that these 120-degree symmetry vortices still exist, but they're always bound into molecules. They're never by themselves. So, for example, the 180-degree ones. still exist. But the 120 degrees have no problem because, oh, go.
See, I have difficulty imagining the system of this tetrahedron. So what do you have in mind? So you have the space filled with objects which look like this.
Yeah.
Can these objects move from one place to another? Are they nailed to each position? Do they interact with each other
Yes,
somehow?
Let's imagine they're nailed, for now, let's imagine they're nailed to each position.
So they can only rotate around that point
Yes.
in some fashion. Do they interact with each
Yes,
other?
and they have an interaction where neighboring ones want to be in the same orientation.
Mm.
So that you want a continuous field of tetrahedron to minimize that. So that's why.
So what would be the physical system which should describe this model?
Well, so I'll get to that in a second. It'll come up in superfluids in a natural way. But just to make it simple, I just want to start by pretending that it could just happen for some reason. So yeah, so basically you want a field that's continuous, which means that if there's a defect, as you go around the defect, the object has to rotate through a symmetry.
Basically, this is a lattice model,
Yeah.
where at each lattice point you have a number of degrees of freedom which might or might not be continuous, right?
Yeah,
Okay.
that's right. So so now I'm applying a magnetic field that suppose that magnetic field wants the tetrahedron to be oriented in this way. Then you can still have a 120-degree vortex where the tetrahedron rotates 120 degrees as you go around this center point. But you can't have a 180-degree vortex anymore because, if you want to rotate this tetrahedron around 180 degrees, it's not going to keep this orientation. I mean, here it never is in this orientation because it started out wrong. You can start with the tetrahedron in the right orientation and then rotate it around this edge I color in black. And then at the beginning it has the right orientation, but all the way in the middle it has the wrong orientation. So the energy of this one vortex is going to be proportional to the area of the system, because this all has the wrong orientations everywhere except over here, along this line. But that problem is solved if you put two of these vortices one next to each other. Because then you can make it so that inside this region, in between them, the tetrahedra have the wrong orientation. But outside the region, they rotate continuously and keep this right orientation relative to the magnetic
But do these vortices want to annihilate because they attract each other?
Is it linearly attracting each other?
Yeah, they're linearly due to this. So you guys both have the question I want to answer now.
Okay.
Yeah. So first of all, they are attracting each other due to this fact that the tetrahedra have the wrong orientation in the intermediate region. So that's coming from this term. That means that there's an energy cost of the order, its magnetic field energy scale, times the area of that region. And to minimize that energy, the vortices want to approach each other.
So there's no stable molecules, per se?
Well, no, but there's another energy cost, which makes them repel each other, and it leads to a stable molecule. Because let's just ignore the magnetic field for a second. If you put these vortices right on top of each other, see, initially, when they're separated, the tetrahedra only rotate to 180 degrees as you go around each of them. But if you put them on top of each other, the tetrahedra rotate through 360 degrees as you go around.
But that's for the vortex of the same vorticity. But if you have positive and negative, they would cancel.
Yes.
So then they want to annihilate.
That's right. So let's say we have ones of the same vorticity.
Oh, then they repel each other. No?
Then they repel each other.
So then how can you have a stable molecule?
Well, the repel each other with, change the color to the,
Oh,
this.
because, I see.
Yeah, there's a logarithm.
Yeah, I got it, thank you.
They repel each other with a logarithmic Coulomb repulsion.
Because each vortex has infinite energy, but so when we combine them, they cancel the extra energy. But, okay.
Yeah, or when it gets worse when you combine them, because now they have the same sign.
Right.
So they'd rather be farther apart. But that's this Coulomb energy. But then, oh, you're talking about the blue, yeah. And when they're right on top of each other, this energy is minimized. So if you put the two energies together, you get a curve with the minimum at a point on the order of square root of k over epsilon. So as the magnetic field gets weaker and weaker, this molecule gets less and less confined. And you basically have free vortices if the magnetic field is very weak. So you basically, as the magnetic field becomes weaker and weaker, you recover the vortices of the rotationally symmetric system. Which is nice because suppose somebody wants to study, is able to make this tetrahedral system, and they want to prove that it's tetrahedral. Even if they can't make it perfectly rotation symmetric, they can still see these vortices that reflect the symmetry of the ground state. Okay, so now let me tell you where this can come up, how you can actually get these tetrahedral molecules. So it turns out that they come up automatically if you make a condensate of atoms with spin. So let's imagine putting a bunch of atoms, say rubidium atoms, with spin 1, and you make an optical trap so that they don't become ordered by the magnetic field. You just have a bunch of atoms with spin 1, and they can have any spin or state, each one of them, that they like. Now, when you usually talk about spin systems, you can have different phases. Like if you cool it, they become antiferromagnetic, or maybe they become ferromagnetic, or different properties. Here you also have, yeah.
A tetrahedron has, in a way, 4 different states distinct, right?
Mm-hmm.
A spin 1, you don't have 3. So how you relate the tetrahedron with the spin 1?
Oh, it won't get it for spin 1. It won't happen for spin 1.
Okay, no, because you said I'm going to show you how this. So that would rather happen for 3 halves.
It's
right?
actually going to happen for spin 2.
2 or not
Yeah.
3 halves?
Well, spin 3 halves you can't make a condensate, so I have to jump to 2. Because it has to be bosons.
Yeah, you can make condensates. It's called Aryan superfluids.
Oh, by pairing. But so okay, so you have those rubidium atoms. And the thing that's neat is you have, if you cool them down, they make a Bose condensate. And that basically automatically means they're going to become magnetically ordered at the same time. Because they're going to all be in the same spatial wave function, but they also all want to have the same spin wave function. And if you choose a spinner for them to condense into, that breaks the rotational symmetry. So it's hard to get a Bose condensate without getting magnetic ordering. So what determines which spinner you get? That's the next question. Well, these atoms interact with a force that depends on their relative spin. So if you take 2 atoms, suppose I have a contact interaction. Then the strength of this contact interaction can depend on the total spin of the two atoms combined. And that total spin can be anything from 0 to 2s, where s is the spin of the atoms. And it actually also has to be even. That's because, since we're looking at contacts, the atoms have to be able to be at the same point. And since they're bosons, that means the spin wave function also has to be symmetric. And that implies the total spin is even. So here's the interaction Hamiltonian. Now let's find what spin or wave function will minimize this energy at mean field. We take the expectation value of this potential in this mean field state. And that gives us like this choric function. And we just have to minimize that, assuming that the magnitude of this spinor is fixed to be the density of the atoms. And that'll determine the ground state. Now, when I was first hearing about this problem, I thought it was a weird problem because you usually think of all the states of the spin one atom as being equivalent because they're all in the same multiplet. Right? That means any one of them can be gotten by linear superpositions of rotations of the other state in that multiplet. But here we have nonlinear interactions, which means that different states of the atom can actually behave differently. So like, for example, you have spin 1. You can take this coherent state, where it definitely has SZ equal to +1. Or you could take a state where SC is equal to 0. And there's no way to rotate this state and get that state. If you're allowed to do superpositions, you can get from this state to that state. But you can't just directly rotate this into that state. Because this state, the expectation value of the spin has a magnitude of 1. And in this state, there's no expectation value of the spin. And so, different states have different properties. In fact, these two states represent the two phases that you can have for spin 1 atoms. If G,
But if you have 1, 0, minus 1 state, it should be equivalent.
yeah, to this one. Yeah, these two states have the same energy. So there's these two phases. There's one where the expectation of S is a vector pointing in some direction, and there's another where the expectation of S is always 0. But as you're saying, there's more than one state with this property. But they're all rotations of one another. And actually, if you think about how to represent them, this one would be represented by a vector, say pointing along the spin. But this one would be represented by a line. Because if you rotate this state 180 degrees around the x-axis, you get itself back up to a phase. So you have two different symmetries for the different cases. And that actually corresponds to these two cases I showed you. So that's for spin 1. For spin 2, you can also find the phase diagram numerically, and you find that there's 3 different phases as a function, I think. Like, I may get the axes wrong. So you basically have three different phases, and this phase is this phase where it's a ground state, it's a coherent state like this, and you have two other phases. But if we want to figure out the vortices of these phases, or the defects of these phases, we have to be able to understand these different phases geometrically. So one approach to do that, I'll show you. So let's imagine we have, oh, sorry, first how it works. Okay, so let's see how to picture a spinner geometrically. The problem is the spinner has, like if it's a spin-s particle, it'll have like 4s independent real numbers in it. And on rotation of an object only has like 3 degrees of freedom. So we somehow have to simplify this complicated spinner. So what you can do is you start with the coherent state. And what I mean by that is you just take this SZ equals S state and rotate it in some direction. And then you define the coherent state wave function. Which is just the amplitude that the spinner you're considering happens to be pointing along the direction n hat. And then the last step is you take this wave function and you map it from the unit sphere, right? It's a function of the direction of the spin, which is a point on the unit sphere. You take that sphere and you project it onto a plane. This is the stereographic projection, right? You take a point on the sphere, you draw a line from the south pole to that point, all the way up until it hits the plane. When you do that, this function turns out to always have the form that function always has a special form. So it has this factor. For spin s, it always has the same factor in front. And then it's multiplied by a polynomial in this complex variable on the plane. And the polynomial has degree 2s. Well, since it's a polynomial, that means it has 2s roots. So you can take those 2s roots and draw them on the plane and then project them back to the sphere. And then use those points to represent the original spinner. So basically like for a special case, take s equals 1/2, then you got 1 point on the sphere. And that's like the block representation of the spin at half particle. But if you have bigger spins, you have more degrees of freedom, so you need more points on the sphere. So let me just show you how it works. Here's 4 different spin 1 spinners. And I want to know which one of these can be rotated into which other ones of those. And I look and I see, well, they all look really different. These two actually look more similar than any of the other ones because they're just different by a factor of I in the middle component. So those are probably the same, but I'm not sure about the other ones. Maybe, I mean,
Question.
yes,
This construction, can I think of it in the following way?
yeah,
I take a number of spin half degrees of freedom.
yeah.
Each one of them is defines a point on the block sphere.
Mhm.
And then spin 1 or spin 2, that's just a projection into a subspace of what's spanned by all these spin halves.
That's right, yeah, you take this.
So you just have some relation between these points.
Yeah, you take, for each point, you can construct a spin a half,
Mm-hmm.
that's represented by that point, and then symmetrize it and you get a spin
Okay.
half. And that's the state.
Mm-hmm.
Yeah, besides, yeah, that's basically right. You have to actually invert everything first.
But is a block sphere actually specific to spin 1/2? So can't I just think about it as a earlier parameterization of the coherent states, which can be defined in any representation of for spin 1, I can have a coherent state will be described by the earlier angles the same way, right? So I don't understand why
Well,
spin half is.
Like you only, like, it only for spin, like for spin a half, every state is a coherent state. Every spin state is a coherent state for spin a half. But if you have another spin, then, well, I'll show, maybe this will help in this picture. Let me see.
So I thought that coherent states are actually abstract objects in
Uh-huh.
principle. You can, and block sphere is associated with basically with I don't know SU2
Uh-huh.
group or something
Mhm.
like that, and it has different representations. One of which is two-dimensional representation, which is spin 1/2.
Yeah,
But that's
But-
special because it's a minimal dimension representation. Those are always special.
No, but block sphere has nothing to do with spin 1/2. That's what I'm trying to say.
or it just has a way to represent. And maybe,
Okay, maybe.
I mean, the black sphere is a way to represent, like, rotation. I mean, it's a good way to get from SU2 to SL3, which is maybe what you're talking about. But, so now I take those four states, I find the roots of that polynomial, and it turns out there's a double root here and here and here, so these three are the same. And this one is different. So maybe this is like kind of what you're asking. These three states are coherent states because they have double roots. This state is not a coherent state, the third state. So just adding that factor of I in the middle component changes the properties of that state. I mean, we sort of knew that, right? Relative, if you change the phases by a relative phase factor, it can change the state.
So what is a unique state now if you have two roots?
Mhm.
It's when you rotate the whole sphere from this and you get the same.
Wait, you mean like,
The one with two roots.
oh, this one here, yeah.
If I move the two roots together, then it's a distinct state. Is that right?
Yeah, if you move them at all, any motion, like, the only thing you
Except
need,
rotating the whole sphere.
yeah, rotating the whole sphere is the same as rotating the spin.
Oh.
But if I take the two roots and move them closer or farther from each other, it changes the spin.
No.
So there's basically, for spin 1, there's one parameter to determine all spinners, which is the distance between these roots. I mean, up to rotations. That determines the spinner. And for spin half, you don't need any parameters because they're all coherent states. And they're all rotations of one another.
So basically, are you saying that this state, which is represented by more than one point, cannot be obtained by rotating, let's say, from the North Pole? Let's say you define a state for spin 1, which
Yeah.
is along the North Pole, in some
Yeah.
sense, up, and then you want to rotate with any SU2 matrices,
Yeah,
so you can generate all the coherent states. So you're saying this state with 2 points is not one of them?
yeah, you can't generate that one.
You can?
No, no.
Oh, okay.
Yeah. You can make it as a superposition of these three, but you can't just rotate this one to get to that.
But if you take this 0, 1, 0 state, it will be also 2 points.
Yeah, it'll be 2 points at opposite ends of the sphere. So then you see that that has a symmetry of a line because you can flip it over. Whereas if you have a double root, then that's like a vector because there's one direction pointing towards the double root. So now if you do that to the phases you get by minimizing the energy for spin 2 atoms, then you find that, so first of all, let's ignore this part. Then you find that over here there's the coherent state, is the ground state. Over here the ground state has 4 points at the vertices of the tetrahedron. And then over here, I'll come back to this now, you find that the ground state is represented by a rectangle, but it can be any rectangle at all, with any aspect ratio. So you have sort of 3 phases. Now this degeneracy of the rectangles is actually an accidental degeneracy, and if you do like higher order corrections, you'll find that there's actually 2 phases in this one region. So like this, the phase diagram was originally worked out in this paper, and then we were just looking at how to figure out the symmetries of the phases.
When was that? 90s?
Yes. Well, I mean, what we did was, no, it wasn't. The original one was probably, 2003, I think. And then we did this thing in 2004. No, 2007. I can't remember. Yeah, it's pretty recent. And then also, just to point out how experimentally realistic this thing might be. If you take rubidium and sodium atoms, the theoretical values for their scattering lengths put them right really close to this phase boundary. So they could either be in this phase or in that phase. And people have studied spin 2 states of the rubidium and sodium atom. The unfortunate thing, though, is that the spin 2 state isn't the ground state. It's like an excited hyperfine state. And that means the time it takes to relax, like to choose between these 2 phases, is longer than the lifetime of that atom. So experimentally, you can't actually get into either of these phases. You'll get it to relax into those phases. But maybe people will find another atom which works better for studying this problem. So, I forgot to say this point. So the summary of what I said about spinor condensates is that they're like multi-component mixtures, but with different symmetry groups. I actually never said that. So the point is, if you have a condensate of spinor atoms, it's represented by a spinor with like 2s plus 1 components. So you can think of that as 2s plus 1 species of atoms mixed together. But the symmetry group is different because for a mixture, each component is separately conserved. They can't change into one another. For spinor condensate, you both have more symmetry because you can rotate a spin up state to a spin down state. But you also have less symmetry because a +1 and a -1 atom can combine together and create 2 spin 0 atoms without violating conservation of angular momentum. So there's both more or less symmetry, depending on which symmetry you're looking at. And then the other thing to remember is that the ground states of these spinor condensates can be represented geometrically, which is useful if you want to find the types of vortices that there are. So I don't know. There's 2 things I can do. Yes.
What happens if you impose an external magnetic field and then you break the rotation invariance?
So if you apply a magnetic field, if it's really weak, you can figure out that it'll orient the state in some way. Oh, I don't have it. So like, with that tetrahedral state, depending on the order parameters, the tetrahedral want to either orient this way or this way. Let's assume the magnetic field is perpendicular to the border. So either the tetrahedral want to be pointing along the magnetic field, or they want to be pointing with the edge perpendicular to the magnetic field. It depends on the scattering lines. But it'll still stay like a tetrahedron. It just has like a preferred orientation.
Mhm. What about the other phases? Do they respond to magnetic field or not?
Yeah, like if you had the spin one, all of them do. Like, I mean, if
No,
you
you
have,
have these 4 different phases. You see
Yeah.
that? So you
Those
you
two-
discuss only the tetrahedron, you see that kind of response. So what,
yeah, these
turn around.
two,
The other way around.
So what happens, for example, you see to the one which is 4-fold degenerate. You see the one on the
Yeah.
right-hand side. Does it respond to an external field, magnetic field, or not?
yeah, they'll all respond. I'm trying to remember. I think it'll want to be perpendicular to the magnetic field.
No, but the one on the right?
This one here?
No, no,
Oh,
yeah.
this one.
Yeah.
Yeah, that one will want to be, well, that one's more funny to explain because it has a magnetization.
What I'm thinking, you see that if you have the spin 0
Yeah,
dominating everything, then probably the system won't respond mostly to weak magnetic fields. The strong magnetic fields probably they would, but the weak magnetic fields probably they'll be insensitive. Is that correct or not?
they have a weak response. Yeah, if it's a weak magnetic field. The thing is, it's a second order response because the total spin is conserved. So you can't just get the spin to go from being in the plane perpendicular to the magnetic field to pointing along the magnetic field, because the total spin parallel to the magnetic field is conserved. And that's because, when you're talking about condensed matter, there's a lot of ways for spins to relax. But in most condensates, if you calculate the lifetimes, they're very long, because they're all due to dipole interactions, which are weak. So basically the spin will want to stay in this plane. And that's what happens. So that one doesn't respond that much. Like, what's more important is what's the total magnetization in the first place. And then these ones are harder to understand because they have that near degeneracy.
Let me ask a more specific question.
Yeah.
Let's assume you have these 3 constants, A0, A2, and A4.
Mhm.
And they make A0 very small, and A2 and A4 very large.
Yeah.
I take them to infinity.
Uh-huh.
So then the preferred state of the system is to have 2 neighboring spins pointing opposite to each other. And essentially you cannot make them do anything else, because if you want to put it in S2 state or S4 state, you have to pay an enormous penalty. So in that case, it looks like the magnetic field essentially won't do anything to the system, so this will behave like a non-magnetic material.
Well, I'm not sure if this is. Let me think. So
So
you're
this
saying
phase
like
diagram,
this
I'll go
phase.
all the way to the left.
Yeah, you
all
go
the way
to
to
the
the
left.
left, and I don't care where I am in this point.
Yeah. Yeah, if it's really huge, I mean, let's say it's not really like infinitely big, because you want the magnetic field.
Well,
to
you
be
know, the
able-
theorists like to do that. You
Yeah.
see, take some constant to infinity, come to 0, and then they solve the problem.
Yeah, so let's just say the magnetic field is a lot weaker than these interactions. Then, like these interactions in this phase, they're getting the spin to be in the SZ equals 0 state. And from what I remember, that state wants to be, I think, perpendicular to the magnetic field, because it's easier to magnetize it. Like the magnetic field wants it to become magnetized, but it's in SZ equals 0, so it's better for it to be perpendicular to the magnetic field, and then it can become magnetized by having these points move a little bit up towards the North Pole. So I mean, everything responds, but sometimes it's not a first order response. Sometimes you first have to deform the state and then have to deform the state and respond to the magnetic field.
So I was wondering about this symmetry analysis, interesting symmetry analysis. So why is it specific to Bose-Einstein condensate? Let's say I have a spin model in the lattice with spin 1 or spin 100 or something like that. So isn't it a way then to classify possible quantum
Yeah.
ground states? Or spin? Where is the condensate here?
Well, it has to be sort of like a ferromagnetic state, where like each site's the same.
Well, is Z equals 0, is it ferromagnetic state? With the single state?
Oh yeah, I don't mean I mean like a uniform state, kind of a mean field state.
Okay, so let's say within the subspace, these possible
Yeah.
mean fields. So are you saying that these are also possible?
Yeah, it should be
So
possible.
where is the actually BEC? Where do you use the faculty of
You're not really using the BEC. I mean, like if you had an anti-ferromagnetic or something, you have to.
breaks.
Yeah, I mean, the point is because it's a BEC, it's uniform. So you only have one thing you have to say.
But you
which
could, in
is
principle,
what's
you could
the
have some
total
kind of entanglement. Well, actually, I think there was a paper of Leggett and somebody else. I think they called it fragmented BECs,
state. Yeah,
which were not as trivial. I don't know.
Yeah.
There was some kind of mixture.
yeah. If you had some kind of fragmented state, you wouldn't be able to use this method. So like this method only works if you have single particle states. Like it won't help you to understand entangled states of two spins.
Right, but what I'm saying is that in principle, you can imagine a lot of uniform phases, not necessarily in BEC, it can be in a paramagnetic state.
Yeah,
But you may say that still it has some sort of interesting spin texture.
yeah, yeah. And you could use this method.
So basically, if you want to write, maybe I translate it to my way, if you write some Landau theory for some magnetic state,
Mhm.
and you ask what's the possible ground states, then this is the answer.
Yeah. This is, but I mean,
That's pretty big then. It's bigger than BEC.
no, but I think the thing is with BECs. So there's two cases where this is important that I see. One is a BEC, and the other is a lattice of bosons, which are interacting by exchange interaction. Because in both those cases, you'll have like ferromagnetic interactions. Like with regular atoms, where it's electronic degrees of freedom, I think each site will want to have like maximum spin usually. Maybe I'm not sure if that's true. I mean, if you have spin a half, then
I'm just thinking about the lattice model of just spins,
Yeah.
no fermions, no bosons, just lattice spin model. Which
Yeah.
You can formulate for spin 1/2, spin 2/2, 3, 5, doesn't matter. So then they, in principle, could have uniform phases.
yeah, and then this would be useful.
But
for
nobody has ever talked, to the best of my knowledge, about distinguishing them this way. So
I think-
maybe it's just, I'm just saying, maybe.
This, the idea of classifying.
Don't
uh,
have spin one. What is
So for your analysis, the quantum nature of these spins is
They're
not
all
really
bosons in
important.
states.
I mean, it's basically geometrical classification.
Yeah.
So I'm wondering if you can get similar solutions, let's say from Landau-Lifshitz equation, from a pure macroscopic magnetostatic equation, which has all the ingredients you need.
Like for a classical work.
Because your analysis doesn't imply any particular quantum dynamics.
Yeah.
It's just geometrical classification.
I think it's possible in principle.
Because there is an extensive literature on that, and they have
Yeah.
all these very intricate solitons and textures. And,
Yeah, right.
so I'm wondering what's the relation of that with what you say.
So people looked at, like they were trying to understand, what you call it, like quasicrystals, using something like this, because you have like icosahedral symmetry and stuff in there. And like I think it's possible in principle. It's just that, like I think it's somehow it's like more natural. Like if you have a bunch of molecules with like the shape of a tetrahedron.
I understand, but you impose a certain crystal symmetry.
Yeah.
Let's say, assuming a certain crystal symmetry, and then you know the form of the Landau-Lifshitz equation is controlled by the symmetry you impose.
Yeah.
And based on that symmetry, you have the static equations for all possible textures.
Yeah,
And if you solve them, I'm just wondering if there's any
yeah, I mean, you could imagine,
one-to-one correlation between what you're saying and
you could have this, you know, you can reinterpret psi as being a classical order parameter.
no, it's different because that is a vector order parameter in Landau-Lifshitz
Yeah.
equation. So
So you couldn't, if you just had a vector order parameter, you can't get this tetrahedron.
that's what I'm asking.
Yes, no, you can't get it. But if you have, you could have like a, kind of a tensor order parameter.
Right.
And then you could get things like this. You know, if the tensor has a high enough spin, or not spin, high enough number of indices, you could get this tetrahedral symmetry. It's just that you have to go to so many indices that it's probably not realistic to happen.
I did some work on that too because people were talking about toroidal currents,
Uh-huh.
and that gives you the tensor order parameter.
Uh-huh.
Macroscopically, just forget about all mechanisms.
Yeah.
And I think there've been some
Yes.
papers on that.
The thing is, I think you have to go, see this tetrahedral order, you get as spin 2, but it's not a perfect symmetry. Like, if I rotate 120 degrees, I get the same state, but only up to a phase. So if you interpret it as a classical order parameter, that phase would actually be like a measurable change. So you actually have to go to like, I don't know, to like spin 6 or something, or you know, which would be like a rank 3 tensor, something. I don't know, some pretty high rank before
I see.
before that symmetry actually happens.
I see.
So, yeah. So I think, I don't know, I can just stop, or no, maybe I should talk about it. Would you like to?
Go ahead.
I can show you a little bit about. I'm trying to decide. So I can talk a little more about this stuff, or I can do something about spin 1 vortices and their dynamics, which I don't know what I should do.
Do you have a coin?
What's that?
Do you have a coin?
You want the vortices? Okay. So I'll just give the summary part of the stuff that I'm not doing. So the summary is that you can classify vortices by symmetry groups. And the reason why is, you know, just this intuitive picture. A vortex, or a defect, is a point where as you go around it, the order parameter rotates around the symmetry axis and comes back to itself. So,
I'm sorry, so
Yeah.
you have this sort of SU2-like symmetry, I don't
Yeah.
know what it is exactly, but also there is a U1 probably due to the BEC.
yeah,
So is there some sort of mixed gauge transform, or they're completely decoupled?
yes. They're actually coupled to each other.
So when you perform this SU2 rotation, let's say, of your points on the sphere, do you have to do anything with the BEC as well to make it gauge invariant?
Yes. So, like a vortex is what you get when the phase changes by 2 pi.
Right.
And sort of a spin texture is what you get when the orientation of the object changes by some symmetry. And it turns out, this is what Ari did, it turns out if you take the tetrahedron and rotate it through 120 degrees, that's only a symmetry up to a phase. So you have to correct that by also having a 120 degree gradient of the phase, which means this spin texture here, where you rotate this to 120 degrees, is bound to a 1/3 quantum of a vortex.
So is it correct to assume that, let's say, if I have not a triplet superconductor, but what's the next one? Is a spin 2?
Yeah, like D-wave.
No, D-wave has a 0 spin. But
You mean it just-
what's the next after triplet anyway?
Yeah.
So that one.
Yeah.
So would you expect similar effects here for
Yeah.
a superconductor with a charged superfluid?
Yeah,
So that would be equivalent of would that be equivalent of that system?
yeah. That's where it first came up, actually, was like David Merman was looking at, I I think the orbital angular momentum of 2,
Ah,
and classifying the possible phases.
But spin 2 superconductor is hard to imagine because you need spin
I
1
know.
electrons.
I know.
Yeah.
Well, no, you have four
Ah,
four electrons. Actually, there are more.
Jean,
Use supersymmetry and do it with them.
So the defects are a mixture of spin textures and vortices, and they can have fractional circulations. They interact with each other due to this term by a Coulomb force. They either want to be as far apart or as close together as possible, depending on which one will minimize the kinetic energy outside. And then if you apply a magnetic field to break the symmetry, that confines them. That confines the defects that aren't compatible with the symmetry, but it doesn't confine the other defects. And that leads to molecules, which are basically asymmetric solutions to the Gross-Pityevsky equation. And you don't have to actually solve the Gross-Pityevsky equation. You just figure out what are the charges of these different defects that you want to put together into the molecule, and then see if the total charge is compatible with the external magnetic field. Because you want them to be able to screen each other, sort of. Remember how there was like that blue region, but when you put them together, the outside is aligned with the magnetic field. You can check whether that's possible.
So if I calculate the energy of that object, it will be infinite probably.
Yeah, the Coulomb energy will be infinite.
No, the total energy of the molecule.
No, it'll be finite if you have the right set of vortices.
Now, on large distances, I mean, at least it'll diverge logarithmically.
Yeah, that's the kinetic energy.
Right.
Yeah.
But you basically kill the main part, the energy proportional to the area,
Yeah.
by combining two
putting it
fractional vortices. That's what
right.
you're saying.
Yes. And then the questions I'm interested to think about is, what are the properties of this kinetic energy interaction due to this term when you have a non-commutative group of vortices? Like, for example, is Earnshaw's theorem still true? From electromagnetism, you have this theorem that if you have an electron, it can't be trapped stably by an electric field. You can have a saddle point, but it's never a stable minimum. It's just an external electric field. And ordinary vortices just interact according to electrostatics. So that theorem's true for them too. But you can ask, will it still be true if you have like these non-commutative fields where you have more degrees of freedom? And then another question is, do you ever get a vortex lattice where the vortices charges don't commute with one another? If you rotate, imagine rotating a spinning condensate. Okay, so I'll go now to spin 1 vortices. So let's take a spin 1 vortex and let's assume it's in the ferromagnetic phase, meaning that the magnitude of the spin is equal to 1 in some direction. If you assume that the total magnetization along the z direction, which is this direction, is 0, then the spin will just be confined to the xy plane. So it would be represented by a vector. Now there's also a phase of that spinner, which you see when you write it out explicitly. So the ground state manifold has 2 dimensions. One's the orientation of spin alpha, and one's the overall phase. Now there's 2 types of vortices corresponding to those 2 phases. There's a charge vortex where theta changes by 2 pi. In other words, all 3 components rotate in the same sense around the center of the vortex. But the spin, in that case, doesn't change at all. It's just parallel. There's also a spin vortex. Let me just say, I'll call this charge vortex a +1 vortex. There's also a spin vortex where the +1 component rotates one way and the -1 rotates another way. That's how it looks if you think of them as three independent components. If you think of them as spinners, then the spin is rotating through 2 pi radians as you go around the origin. But you can think of both of these as bound states of vortices. This is a bound state of 3 vortices in the 3 components, and this is a bound state of a vortex and an anti-vortex.
Alpha rotates by pi or by 2 pi?
What's that?
Alpha rotates by pi or by 2 pi?
By 2 pi. You can,
Because I think
you can rotate.
if you rotate it by pi, you get equivalent speed, right?
No, because it's this is a vector. That happens for a pneumatic state. But here it's a vector, so if you rotate by pi, you'll get the magnitude of the spin. The expectation of the spin opposite, rotating in the opposite direction, pointing in the opposite direction. So,
And that's what Simulacraf was making statement that actually if you add another phase to this and not to the middle component, and if you rotate them too, then actually it's enough. But he was making a statement that energy of this vortex will be like a factor of 2 times smaller because you can rotate alpha not by 2 pi by pi, but simultaneously you rotate another angle in some way.
I think that might be the other phase, that pneumatic.
Right. Yes, probably. And he was saying if you combine the two,
Yeah,
you will
then you
get the
lower the
vortex
energy.
is low energy.
That's right. But that's the other phase, I think.
Okay. Oh, this will be polar phase. probably.
Yeah, the polar
Okay.
phase.
So I'm wondering, so algebraically, when you study, let's say, energetics of this thing, so what do you write? Basically, is this phenomenological Ginsburg-Landau type expansion or Gross-Pitayevsky-like thing? So
Yeah, it's not even that. I'm just assuming, that the spinor keeps the form. I'm minimizing this v of psi, and then calculating this grad
Psi is just a
squared.
multi-component order parameter.
It just comes out to be basically the Euler angles. The order prime is just the Euler angles.
But what dimensionality of the psi?
Oh, yeah, psi is multi-component.
So, but why
But
can't
I'm
I
not
have
actually-
a matrix K there? So, in principle, nothing prohibits me from having some sort of a operator like.
Oh, here.
Yes.
Well, if you have the road like the SU2 symmetry, that just has to be just one number. Like if you have a mixture, it could be different components. It could be a matrix. But if you have a spinor condensate, the SU2 symmetry means it's one number. But it's h bar squared over the mass of the particle.
So Jan, you said that you fix somehow the spinners locally. Is it? I mean, if you have without kinetic energy term, you have a certain spinner, then you are making a statement that, I mean, if you go to another position, that it's simply the same spinner but rotated by some angles. Okay.
Yeah.
So you rule out the possibility that the kinetic energy term would somehow be strong enough that, I mean, it would actually imply that you might have a different phase in some part.
Just, yeah, most of the condensate, the phase will be the same. Just in the center of vortices, the kinetic energy would force it to be a different phase. But I'm not focusing much on that.
But I'm sorry to return to the same question, but in the gradient term, when you do rotation, so SU2 is actually rotation in real space, you have to rotate not only psi, but also the gradient.
But that's only if you, that's a good question, yeah.
So you can actually have some kind of non-abelian in some sense
Yeah.
structure.
But that's if you had some kind of a spin-orbit interaction, like if the dipole interactions are important, or something like that, then you have to rotate space and spin at the same time. But usually in like this cold atom
So
stuff.
this is not the real
It's
SU2
not important.
rotation in the real space.
Yeah, it's just this
Okay.
rotation of the spin part. And that's a pretty good
So-
symmetry. Yeah. Okay, so let's see these. We have these two types of vortices. Let's see how they move.
So what's the minimum dimensionality of the order parameter you need to get those?
Like,
How many components do you need to get this thing?
yeah, depending which one you want, you need more components. I mean, just if you want a tetrahedron.
No, it's a two-dimensional, right? system.
So for this, you need three components.
Three
And
components.
it's a spin
So
one.
that's the minimum. The minimum.
Yes, the minimum one for this is spin
Okay.
one. So let's see how these vortices move. If you think about the charge vortex, it's just like a vortex in helium-4, where there's no, spin structure. And those vortices don't act like regular particles. If you apply a force to a vortex in helium, it doesn't move along the force, or it doesn't even accelerate along the force like you would expect from Newton's laws. It moves perpendicular to the force. And that's because of the Bernoulli principle. And I'm not ignoring friction, so otherwise there would be a small angle. But the point is, the velocity of an ordinary particle, of an ordinary vortex, is determined by the force, not the acceleration, like you would have for a Newtonian particle. So in particular, there's no inertia. If there's no force, the vortex would just sit in one place. How do I know that? Let's imagine this vortex were moving. Then it would be like a baseball with like some spin. And it's moving relative to the fluid. When you combine the relative motion to the spin of the vortex, you have a higher pressure on one side, a higher velocity on the top and a lower velocity on the bottom, which means by Bernoulli's principle that the pressure is higher down there and it pushes the vortex up.
But vortices have mass. I mean, if you apply, let's say, time-dependent field, you'll behave as a particle with a mass.
It would have a mass, but it also has a really strong, like, Magnus force.
Right, I understand.
Yeah.
But if you don't have dissipation, then the velocity will be proportional to the velocity of the current. So it will be proportional along the current direction.
Yeah.
But if the current changes with time,
Yeah,
then you'll have some inertia
yes.
in the vortex. It
That's-
mostly comes from the vortex core. But
There's some inertia, but there is an inertial motion. Like the vortex, if it starts to move, it'll feel a lift force. So if you take the inertia into account, it would go around in a little circle. It wouldn't keep going in one direction. And I'm just going to take the limit where the mass is really small, just to simplify it. Okay, now, how does that change for a spin vortex? This is one of my professors on my committee asked me this question, and so I thought about it. And the point, so you can just think about it from Bernoulli's principle. Think about the vortex as being a bound state of a vortex and an anti-vortex. Right? A spin vortex is a bound state of a positive vortex in the top component and negative vortex in the bottom component. That means that if the vortex is moving, these two components feel Magnus forces in the opposite direction. So when you add them together, they just cancel out. So that means there's no Magnus force. And now, what's that?
They can separate?
Oh, I'll tell you. That's important. Yeah, so let's pretend they can't separate first. So now there is no Magnus force, which means that even if there's a really small mass to the vortex, that's going to be the dominant effect. So first of all, we know that a vortex, if it starts to move, it'll keep moving because it won't experience any external force. And then we also have Newton's second law, which says if there's a force, maybe there's another vortex around and they're interacting with each other via like a Coulomb's law. Then this vortex responds by Newton's first law. So that's just a guess, since there's no velocity response to the force. The next simplest thing to assume is that there's an acceleration. Okay, but there's a problem with that, it seems, because if you look at the energy function of the spinor condensate, here it is no psi dot squared term. So where do you get kinetic energy, which is what you'd have if you had Newton's second law? Okay, I'll answer that in a second. But I also have to point out another important thing, which is that, what is it that's preferring the particular form of the spinner that we have? It's this spin-dependent energy term. And that wants the phase of the top component and the phase of the bottom component to be opposite of each other all the time. So, okay, so now back to the question of where's the kinetic energy? There's another paradox besides that one. Because I'm claiming that these spin vortices move inertially. But I'm also claiming that they're bound states of two ordinary vortices. And I know that ordinary vortices don't move inertially.
Sure, but to define kinetic energy, you need an action, not really an energy. It's some kind of action with time dependence that you would want to write instead? With a
Well, you can think of this as the Hamiltonian of the system. And then psi and psi dagger are canonically conjugate to each other.
Oh, okay.
So then you can derive from this equation the Gauss-Penyatsky equation for the spinor compensate. But that would be a first order differential equation. But we need like a second order, something second order to get the acceleration.
And is this the most general form that you could possibly write? Or it's just a reasonable one?
It's because the interactions are so weak, you can basically derive this. Like, this comes from the spin-dependent scattering that I was talking about at the beginning, this term. And like this term just comes from the average scattering of two particles. So, I mean, it's not the most general form, but you can actually derive it pretty accurately. So the answer to how do you get a spin vortex to move inertially is exactly what you're asking. Let's take the two vortices making the bound state and separate them to a certain distance. So we put one here and we put the other one there. Then in the region in between, the spinner doesn't have the right form, which means that green term in the Hamiltonian has a bigger value in there. So there's some energy in this region. It's just like what I was talking about at the beginning, except that I drew the wrong colors for it. You're breaking you have an energy cost from not minimizing this extra term in the Hamiltonian. And that means that when you separate the vortices, there's an energy that's proportional to the area of that region. And that means that there's a force trying to pull them back together, which is the derivative of that energy, like a Hooke's law kind of a force. But if this vortex is being pulled down by that force, then the Magnus force law, because it's an ordinary vortex, the Magnus force law applies, means that the Magnus force means that that vortex will move to the right, perpendicular to the force. And the same thing, if you work it out, happens to this vortex. It also moves to the right. So the vortex molecule as a whole moves to the right. And the speed is proportional to the force, which means the velocity is proportional to the spacing of the two component vortices. If you substitute that back into the energy, you find that the energy goes as the velocity squared, and that's your kinetic energy. And you can read off the mass and see that it's proportional to 1 over the spin-dependent interaction strength of those two vortices, of the atoms.
So would you have an oscillatory motion there in the end? Because they'll come together and they'll continue moving and then go back and forth,
Well,
and then they'll go back and forth in this direction.
No, you don't have the oscillatory motion.
So what will
because
happen when they come together?
They don't come together because the way they respond to the force is they move perpendicular to it.
No, but they also
No, but
attract
you
each
said
other.
that they move towards each other.
Or they want to move towards each other, but they don't.
No, can you turn around?
I thought you were showing me the vortex. Yeah. The force is going this way, but they move perpendicular to the force.
Yeah, but what prevents them from just annihilating?
Because there's no friction in the system. So there's
No,
way.
they attract each other, right?
Yeah, but the way a vortex moves is it moves perpendicular to the direction.
Oh, you mean with no dissipation, they would just rotate like this?
Yeah. Well, in this case, they go
Straight.
parallel to each other.
Right,
because
right,
of the
right,
science, but- Yeah. Yeah, it's a weird. I mean, vortex dynamics is completely weird compared.
No,
to
it's a vortex dynamics in an ideal liquid.
Yeah.
You know, in any hydrodynamic book you have that,
Right.
like exactly this thing.
I think this is
Yeah.
classical hydrodynamics too, right?
Exactly. That's
Yeah.
what-
Yeah. It's
Like
classical.
vortex, like if you take one vortex near the surface, there's an image to,
Yeah.
to provide the boundary, so vortex will move parallel to the surface because of that.
Yes.
It's the same thing.
Yeah.
But
Yeah.
usually there is no mass to it.
The
Right,
difference-
so it's an ideal liquid.
Yeah.
But here somehow there appears a mass. Which
So the
It's a
difference
kinetic
is-
energy, that's how he defines it, but it's not a real
Yeah,
mass.
I'm defining the interaction of those vortices as being the mass, or the kinetic energy. But wait, there's one important thing. So in the example, in what you're saying, the force pulling the vortices together is like the 1/r like Coulomb force between them. And in this case, the interaction is proportional to the distance because it's coming from these spin-dependent interactions here. So, like that leads to the energy proportional to v squared. Like in like the case of a vortex ring or like a pair of vortices, I think the energy goes like 1/v or something. It has the opposite sign. So you can't think of it as a kinetic energy in that case.
in which phase it is, this statement?
In the ferromagnetic phase. So.
But in the ferromagnetic phase, if you write sort of Ginzburg-Landau type expansion,
Uh-huh.
so the term with the quadratic s should be negative in some sense, no? And there should be some. Well, if you
Yeah,
do just
yeah.
that sort of only if you concentrate only on the spin-dependent part and just
Yeah.
do Landau theorem, not on Ginzburg-Landau,
Yeah.
should you get an instability basically defined as?
Oh, you-
This coefficient is negative.
Yeah, it is coefficient. Beta is negative.
Oh, is it negative?
Yeah.
So the mass is
Yeah.
negative.
No. Oh, I just.
Oh
No, I put it absolutized.
Oh, okay, yeah, sorry. Okay.
The beta is negative, and what happens is I'm looking like I'm most interested in like the SX and SY components, which will give you when you square it, they give you something like times beta. And if you look at how that depends on the phases, it's something like that. So to minimize this energy, you want the cosine to be equal to 1, which means the phase of the middle component has to match the average of the phases of the top and the bottom component.
Mm-hmm.
And that's why, like, if I try to separate these vortices from one another, then the phase isn't right anymore in this middle region. So
But,
that's what that energy
For instance, when you have a Magnus force, let's say you run a superfluid, basically, and you have a perpendicular force on the vortex, right?
Uh-huh.
So if you have, let's say, a spin current in some sense,
Yeah,
gradient of S,
yeah,
would it also experience a Magnus force? The
yes.
vortex.
If you apply a spin current, that'll give you a force for these spin vortices. And that's a way, like if you want to see them accelerate, you could put them in a spin current. And, oh, sorry, wait, let me go back. You'll see a force, but it won't move perpendicular to force. It'll actually accelerate along the force.
But that
Just
would
like
be
you
that would be
expect.
unstable with respect to any dissipation because that would give you the component perpendicular to the force.
Yeah, dissipation would change.
So no, dissipation will just result in annihilation of this thing.
Well, they're in different
dissipation.
components. They're
Any
in different components. Oh, I should have said that. I should
No,
have said that.
then the force is no longer along the velocity, so it will be a component perpendicular. So this force will push them together.
Yeah, but that I think that might just give like some kind of a drag term in the equations.
No, I
You
mean,
just
they're no
cancel
longer
this
stable.
mass essentially, because I somehow associate the fact that there is no mass with basically gauge invariance, and it's
Uh-huh.
perfect superfluid when you run. Well, you have a Magnus force. You run the superfluid, you have a force. So here, in the same fashion, since the space is entering sort of symmetrically, if you run a spin current, you will generate a similar force.
Yeah.
So, but you're saying somehow you get a mass which is associated with the spin.
Yeah.
Okay,
Yeah.
I don't know, maybe it's wrong.
I have to think the difference.
There's one extra thing. I mean, if this is in a BEC, I mean, it would be in a trap in the end. And I mean,
It could be
Yeah.
right.
it would be in a trap, so the density is inhomogeneous.
Yeah.
So if you have a vortex there, I mean, it would start, I mean, depending on circulation, it processes either counterclockwise or clockwise.
Yeah.
In this case, it would somehow seem that your plus vortex goes one way and the minus would go the other, so there would be something extra because of that somehow. I mean, of course, it disappears in the limit where trapping frequency goes to zero.
Yeah. Well, you could think of the trap, like if you, instead of thinking microscopically, like what's this vortex made up of, just think of it as a particle. And then the trap would give you some force that wants the vortex to move towards the edge, because that's where the vortex can be the shortest and wants to minimize its length. So you'll have a force that points towards the edge somehow. Maybe it's just proportional to the radius. And then you'll have Newton's law. So it'll just accelerate out to the boundary. So that's the difference. Instead of, with a charge vortex, it would circle around. But with the spin vortex, it should accelerate out towards the boundary if you start from rest.
But this implies that in a real experiment they should see that spin vortices disappear very fast. But I know in the Settler experiments that's not the case.
Well,
Vortices are stuck there for a very, very long time.
I know what you
And
don't.
those are regular vortices.
They're not regular.
They have some
No,
spin
no.
vortices.
An experiment.
Oh, they found lots of those.
Like this.
Yeah.
I don't. But there's like a whole bunch of other.
Yeah,
Right.
It's not
but,
like a
I mean,
perfectly
something
uniform-
stabilizes them because if they would be like particles, they would probably disappear very fast because they're not favorable, but they're stuck for a long time. So
Well,
it's something which keeps them inside.
The mass is pretty small, also.
That way.
So, well, no, pretty big. Yeah. I think.
I'm just confused because your model is Galilean invariant, right?
Yeah.
So you don't have any trap in your model, you don't have any boundaries, you don't have anything. So you just have a flow, and you can go into the system basically with the flow, and there should be some sort of Galilean transform that you should be able to perform
Yeah.
with your action.
Yes.
So wouldn't it do the same thing that it is doing in a normal BEC?
Well, you can't get rid of the spin current by doing a Galilean transformation. So if you have a charge current, like,
You have uniform phase, which you assume you do.
yeah,
So then it should be invariant.
the spin current's invariant.
So how? Okay.
Right.
Just that-
This is simple. Yeah, I think there's a good point to make about that, but I forgot. I'll think about that. But I mean, you don't. Yeah, I'll think because there is something interesting about that. But basically, the summary is that charge vortices, if you neglect the mass, their equation of motion is a first-order differential equation, which means you need 2 degrees of freedom to describe a charge vortex. And for that, you can just use the position of the center. For a spin vortex, the differential equation is second order, which means you need both a position and a momentum. And what are those? Well, the position is the center mass of the 2 vortices, and the momentum is proportional to the dipole moment between them. And that's that. Oh wait, before saying that's that, I should just summarize. So, basically you can get a lot of interesting stuff about spinor condensates without doing detailed calculations, because they're complicated enough. They have enough degrees of freedom that there's a lot of interesting things to study just at a very geometrical level before you get into the real details. So that's the nice thing, I think, about studying spinor condensates. Oh, now I'm done.
Questions?